Hey guys, so the final circuit that we will look at is this mixed series and parallel combination. So here I've decided to put the 220 ohm resistor in front and then make a parallel combination of 100 ohms and 330 ohms. And like we've been doing in the previous two circuits, we will make this circuit and see if our voltages measured are correct. Again, follow the same technique. So the first thing we do is that we find the total circuit resistance. Now, it's a bit less trivial because this circuit contains both a parallel component and a series component. The parallel component is here, but once we find out what the equivalent series resistance that this parallel combination makes, we will effectively have two resistors in series. Let me do that in purple. We'll effectively have two resistors in series. So we'll have this resistor in series with that resistor once we find out what the total resistance of this parallel combination equates to. So first we find the parallel part, and the parallel part is made up of two resistors, so we use this expression here, put the numbers in, and we get a total resistance of 76.74 ohms. And this parallel combination is basically equivalent to a single 76.74 ohm resistor. Now we have, effectively, we have a resistor with 76 ohms in series with a resistor that has 220 ohms. So now we can use the more straightforward series resistance expression to find out what the total circuit resistance is. So this single 76.74 ohms resistor is in series with the 220 ohm resistor. So RT equals R1 plus R2, put the numbers in, and we get a total circuit resistance of just shy of 300 ohms. Now that we have the total circuit resistance and we know what the total voltage is in the circuit, 5 volts, we can use Ohm's law to find out what the total circuit current is. So 5 divided by 296 gives you 0.016 amps. Okay. Now, this current here, it flows from the battery. So 0.0168 amps. That same current will pass into this resistor. Then when it reaches the junction, it splits off. So let me call that I2 and let me call that I3. And I1 is here. So I2 is going to be 0.016 divided by some factor, and I3 is going to be 0.0168 divided by some other factor, but both of them together will still add up to 0.168. First of all, let's calculate the voltage dropped across the 200 ohm resistor. So V equals IR, so 0.0168 times 220, the voltage dropped across the 220 ohm resistor will be 3.69. Let's just say that that's 3.7. So 3.7 volts will be dropped. Now, due to Kirchhoff's second law, we already know that since 3.7 volts is lost, therefore 1.3 volts should be lost here, and 1.3 volts should be lost there also. Basically, 1.3 volts will be lost across this entire resistor. So that's a V. So 1.3 volts will be lost there, and 3.7 volts is lost there. So both of these resistors will take 1.3 volts each, irrespective of exactly how much current is going through them. Now I've ignored calculating them each or calculating the currents. Well, actually I did it. I forget. So I reason here that because of R1, we already lost 3.7 volts, so there is 1.304 volts for the rest of the circuit. We can already predict that 1.3 volts will be dropped on both V2 and V3, or R2 and R3, basically these two resistors here. And I set about calculating what current they should each have. I say that 100 ohms is about a quarter of the total resistance that both resistors make together, so it should get about 76% of the current, whereas the 330 ohm resistor should get about 23% of the current. So I calculate what those percentages means in terms of current. Then I go about proving that, or determining that, therefore the voltages are basically identical. So once again, let's make this circuit and calculate the voltages dropped across each component. So for the last circuit, here we have is the mixed circuit. Now these are actually the wrong way around, and I use quotations over wrong because it doesn't matter. It doesn't matter that the parallel part is closest to where the power comes in and the series part is closer to ground. It doesn't matter. Voltage is still going to be dropped the same way. So in parallel, I have the 100 ohm resistor and the 300 ohm resistor. And in series to all of that, I have the 220 ohm resistor. And here's how it looks sideways. Okay. Just to double check, let's measure the resistances. Now it becomes increasingly difficult to measure resistance on a breadboard, but we'll try. So let's click that there. Should auto range, measuring about 200 ohms, and that's the 200 ohms as in the theory. This one should read 100, I believe. It doesn't. I have a feeling that that same value will be read there. That's what, because I already tried this before I started recording, so it's quite hard. Yeah, okay, fair enough. So let's turn on power. And in the theory, we predicted that the total circuit current would be 0.016 amps. The voltage lost on the 200 ohm resistor would be 3.696 volts. The voltage lost on the 100 ohm resistor would be 1.2. Well, they'll be both the same. These would have identical voltages lost, but they would have differing currents. So the current in the 100 ohm resistor branch would be 0.01289 amps, and the current in the 300 ohm branch would be 0.0039 amps. First of all, let's check the voltages. So change that to DC. So measuring across the 200 ohm resistor, and we should read about 3 point something volts. 3.69 volts measured across the 200 ohm resistor. 3.69 exactly, actually, which is very good. Okay, so on both of these, we should measure identically 1.289 volts or something close. .29, that's pretty much bang on. And on this side here, 1.29 volts again. Very nice.